next thing that we wanted to have a look at is measuring distances indirectly. Now, why we have these sort of techniques is because sometimes it's impossible to measure how big something is, like a pond here, because you can't measure directly across it. Now, I've never been able to walk on water, so I'm not going to be able to use a tape measure to go across the pond. So we come up with techniques that can be used to allow us to figure out how big the pond is or how long it is without actually having to measure it directly. So the first technique we're going to look at is we can actually create a triangle around the pond. So what they've done here is they've measured up from X to Y far enough that they can then draw a diagonal line down so that Z is in line with X. And what happens then is you then create a nice right angle triangle. Now, with a right angle triangle, we can then use things like Pythagoras' theorem. So in this case, what they do is they measure ZX. So they're looking for ZX, sorry. So XY, they measure to be 18.4 meters. And ZY, or YZ, they measure to be 65.2 meters. So you've got to be a little bit careful because everyone knows Pythagoras' theorem is a squared plus b squared equals c squared, but sometimes it's not c we're looking for. So I label the sides, so I've got A, B, C, and what we can see is that we are actually looking for the side A. We need to change our formula a little bit. So Pythagoras says that A squared plus B squared equals C squared. Now if we're looking for one of the others, what we can do is take it away. So we can say that A squared equals C squared, take B squared. So all I've done is move that onto this side, and to be able to do that, I have to take it away. So what's happening here is A squared will equal the square, well, A will equal, because it's squared there, the square root of 65.2 squared take 18.4 squared. And if we do all that and put it into our calculator, we end up with 62.5 meters. So what they find is that ZX, which is this horizontal distance, is 62.5 meters, and they didn't have to measure it directly. Now this is one technique that they use. There is quite a few others they can use. Perhaps the simplest of the lot, realistically, is this one. All they do is they measure straight up and then straight across. Let's put a big rectangle around it. Now, this isn't always feasible because there could be things like trees or forests in the way to make it so you can't do it. But if you can do it, it's by far the easiest. Because what we then know is RQ equals SP. In other words, the top horizontal one equals the bottom horizontal one. And we can easily measure the top one, which is RQ. There's no working out for it. You just actually measure it. Another technique they've used using a triangle is this one here. And this is actually using a concept called similar triangles. So what they do is they actually measure a triangle up like here and here. And they make it go far enough that they can create this line DF. It's very important. So that line DF has to be above the edge of the pond. And what we can say is that you'll see that DC, this little bit here, and ED are actually the exact same size. That's why they've got little dashes on them. So how this helps us out a lot is that we can now say that the distance EC, so the big triangle, is double the smaller one. So EC equals 2 times ED. In the same token, GE, which is the other side, will equal 2 times FE. So with that concept in line, we know that GC then has to equal 2 times FD. So all they have to do, sorry, it's meant to be a D. All they have to do is measure what FD is and then times it by 2. So again, a very simple technique that surveyors can use. These 3 techniques are relatively simple mathematically, but they are not always useful. Now the reason why they're not always useful is sometimes there's obstacles you can't get around. Now the example here is the main road. Now you can't measure to the end of a lot of main roads because they go on for kilometres. So rather than do that, they use what's called sighting poles. So these are really big long poles they hold up vertically to the ground. So like a pole going up PQ. Okay? And what they can do is they can hold up these poles and they shoot a line from T to S. Alright, so that's this big line here. And you'll notice that it cuts this line here perfectly in half. And that's the important part. It has to cut it perfectly in half. Because if it cuts it perfectly in half, we can then say that this line here is exactly the same as this one here. So to write that mathematically, we can say that QS equals TP. So these are just some of the surveying techniques that are used to find out what distances are. Now, one of the ones which isn't done very well, or explained very well in the examples in your book, is what do we do with something like this? Sorry, just bear with me, please. So if we have something like this, you'll notice that they didn't cut it in the middle. Okay, so these 2 distances are different to each other. And that makes our life harder. But what you've got to realise is that these are 2 similar triangles. Okay? That's the nature of this. We're creating similar triangles. So to make that easier for you to see, that's the little triangle. And if I turn the big one around, the big one looks like, just checking, make sure I got the numbers right. So, what we're going to use here is a ratio. So the big one is just a ratio bigger than the small one. So we've got to figure out the scale factor. And what we do is we compare similar size to do that. So this one here gets compared to this one here. So what we can do is the scale factor equals 47.2 divided by 25.4. Now we get out our calculator. We do 47.2 divide 25.4. You'll see it's a very big number, but we'll just round that out to 1.86. So that means that the big triangle is 1.86 times the size of the smaller one. Okay? So if we can figure out what Km equals, we know what Lj will equal. Now when we're looking at this, we got a combination of a couple of concepts here. So if I look at the small triangle, we are looking at Pythagoras. squared. This is A, B, C. So we know that A squared equals C squared take B squared. So we know that A equals the square root of 56.8 squared take 25.4 squared. So 56.8 squared take 25.4 squared equals, I think we want that one. And we get 50.8. So I know that this one here is 50.8, and we know that this one here is 1.86 bigger. So therefore we can say LJ equals 50.8 times 1.86, and we get 94.488. So for some of these harder questions, you really need to realise you've got to combine a couple of ideas.